Right now, 642 light-years away, a star 700 times wider than our Sun prepares for the most spectacular death in human history. You think space is calm and predictable. However, the cosmos around us seethes with violence beyond imagination. Tonight, we journey through plasma highways carved by ancient explosions, past rogue black holes hunting through our galaxy toward microquasars firing particle beams at impossible speeds. We will witness a hidden companion star that delays cosmic destruction, explore tunnels connecting distant worlds, and discover why our night sky stands on the brink of transformation. Prepare yourselves. We begin. Scientists stared at their screens in disbelief when they finally spotted the ghost that haunts Betelgeuse. For decades, astronomers watched this red supergiant dim and brighten in mysterious cycles. They believed the star was dying, carbon burning in its core like a cosmic time bomb. However, the truth shocked everyone who thought they understood stellar death. Meet Betelgeuse, the blue-white companion star that nobody saw coming. This stellar partner orbits Betelgeuse every 2100 days, acting like a cosmic snowplow pushing through dust clouds. Think of a speedboat cutting through water, leaving waves behind. When Betelgeuse plows through the material that Betelgeuse constantly throws into space, it creates the brightness changes we see from Earth. The discovery happened using the Gemini North Telescope with special speckle imaging technology. Scientists peered through the blinding glare of Betelgeuse itself to find this hidden companion. The blue-white star shines much fainter than its giant red partner, like trying to spot a candle next to a stadium floodlight. Here comes the shocking part. Betelgeuse was supposed to explode in tens of years. Astronomers predicted imminent supernova based on the brightness cycles they observed. The companion star changes everything. Those cycles happen because of orbital mechanics, not internal stellar collapse. Betelgeuse extends Betelgeuse's lifespan from decades to hundreds of thousands of years. When Betelgeuse eventually does explode, the show will be unlike anything in recorded human history. The supernova will blaze at magnitude -10 to -12. Imagine a star as bright as a half moon, visible in broad daylight for months. You could read a book by supernova light at midnight. The explosion will cast shadows on Earth from 400 trillion miles away. Betelgeuse spans 700 times our Sun's radius. If you place this monster where our Sun sits, the stellar surface would extend past Jupiter's orbit. Material from recent surface explosions equals 400 billion solar flares combined. The 2019 to 2020 Great Dimming event saw 40% of the star's light blocked by ejected dust clouds. Current measurements place Betelgeuse at exactly 642 light-years from Earth. The supernova poses no danger at this distance. However, neutrino detectors will give us 10 to 15 seconds advance warning before the light reaches our eyes. We will literally see the future arrive. The companion star discovery rewrites supernova prediction models. Binary systems behave differently than single stars. Mass exchange between stellar partners affects nuclear burning rates. Orbital mechanics influence stellar winds and dust production. What seemed like death throes were actually gravitational dance moves. Betelgeuse teaches us that even the most famous stars harbor secrets. The night sky looks static from our perspective. Stars appear fixed in constellation patterns passed down through millennia. Yet, stellar systems evolve in complex ways we barely understand. Multiple star systems dominate the galaxy, with single stars like our Sun being the exception. This discovery opens new questions about stellar evolution and supernova timing. How many other giant stars have hidden companions? What other assumptions about stellar death need revision? Betelgeuse may surprise us again before its final performance. However, what approaches from the depths of space makes Betelgeuse look like a gentle neighbor. In 1.3 million years, an orange giant will dominate Earth's night sky, like no star in human memory. You look up at the constellation Serpens Cauda today and see nothing special. The star lurking there appears so faint you need a telescope to spot it. Yet this cosmic sleeper will become brighter than every star we currently see combined. Gliese 710 creeps toward us at 43,000 miles per hour. This orange dwarf star currently sits 63.8 light-years away in the constellation Serpens. Its magnitude of 9.7 makes it invisible to naked eyes. Amateur astronomers struggle to find this unremarkable K7V class star among thousands of similar faint points. The approaching encounter will rewrite Earth's night sky completely. Gliese 710 will pass within 0.166 light-years of our solar system. That distance equals roughly 10 trillion miles, closer than any star has come in millions of years. The orange giant will blaze at magnitude negative 2.7, matching Jupiter's brightness and outshining Sirius by 4 times. Picture this cosmic visitor growing brighter night by night. Unlike every star you see now, Gliese 710 will appear as an actual disk rather than a point of light. The approaching star will become 140,000 times brighter than today. You could watch it move visibly across the sky at nearly 1 arc-minute per year, like the moon drifting past background stars. Gliese 710 will reign as Earth's brightest star for nearly 20,000 years. The encounter transforms more than just brightness records. This stellar visitor will plow through the Oort cloud like a wrecking ball hitting a house of cards. Gravitational forces will scatter trillions of icy bodies in every direction. The Oort cloud surrounds our solar system like a spherical shell of frozen comets. These ancient remnants from solar system formation orbit at distances up to 100,000 astronomical units. When Gliese 710 passes through this cosmic debris field, gravity will fling countless objects toward inner planets. Computer models predict 10 comets annually will cascade toward Earth and Mars for millions of years following the encounter. The late heavy bombardment that scarred planetary surfaces 4 billion years ago will essentially restart. Impact craters will pepper every solid surface from Mercury to the asteroid belt. The orange star measures slightly smaller than our Sun, with roughly 60% solar mass. Its surface temperature of 4,000 Kelvin gives Gliese 710 the distinctive orange hue that will paint our night sky. Spectroscopic analysis reveals this star burns hydrogen steadily, with no dramatic variability or stellar flares. Advanced civilizations around distant stars probably spotted our Sun approaching their systems millions of years ago. They watched our yellow star grow brighter in their skies, just as we will observe Gliese 710. Perhaps they prepared for gravitational disruption of their own comet clouds. The encounter rate between stars in our galactic neighborhood averages 1 close passage every few million years. Previous visitors reshaped the Oort cloud repeatedly throughout Earth's history. Mass extinction events may correlate with these stellar encounters through increased comet bombardment. Gliese 710 brings no radiation danger due to its stable hydrogen burning. The star produces no harmful X-rays or gamma radiation that could damage Earth's atmosphere. Solar system dynamics face the primary threat from gravitational perturbation of long-period comets. Yet even this approaching stellar giant pales compared to the architectural marvels that ancient explosions carved throughout our region of space. The space between stars hides a secret highway system that connects our solar system to distant worlds. You imagine interstellar space as empty darkness punctuated by isolated points of light. This picture is completely wrong. Ancient stellar explosions carved vast tunnels through the galaxy, creating channels of superheated gas that stretch for thousands of light years. Scientists using the E-Rosetta X-ray telescope discovered these cosmic highways by accident while mapping background radiation. The space around our solar system glows with million-degree plasma that should have cooled down long ago. Instead of random hot gas clouds, the observations revealed organized structures pointing in specific directions. These interstellar tunnels formed from multiple supernova explosions that occurred over millions of years. When massive stars explode, they blast shells of material outward at thousands of miles per second. Imagine throwing a rock into a pond and watching ripples spread across the surface. Stellar explosions work similarly, except the ripples are shock waves of superheated plasma expanding through space. Multiple supernovas in the same region create overlapping blast zones. The expanding shells collide and merge, carving channels through the interstellar medium like rivers cutting through landscape. These cosmic waterways follow paths of least resistance, connecting regions where ancient star formation occurred. The local hot bubble surrounding our solar system extends 300 light-years in diameter. This cavity contains gas heated to 1.2 million Kelvin, roughly 100 times hotter than the Sun's surface. The bubble formed when nearby stars exploded between 10 and 20 million years ago. However, the local hot bubble does not exist in isolation. Tunnel-like extensions connect our cosmic neighborhood to distant stellar regions. The most prominent tunnel points toward the constellation Centaurus, potentially providing a direct pathway to the Alpha Centauri system 4 light-years away. These plasma highways offer fascinating implications for interstellar travel. Spacecraft could navigate through low-density channels rather than plowing through normal interstellar space. The tunnels contain roughly 1/10 the particle density of surrounding regions, reducing drag on hypothetical starships. The tunnel network resembles the cosmic web structure that organizes matter on galactic scales. Just as dark matter filaments connect galaxy clusters, these plasma channels link stellar neighborhoods. The architecture suggests that supernova explosions follow patterns related to spiral arm dynamics and star formation history. Scientists discovered similar tunnel systems around other nearby stars. The network may extend throughout the local galactic arm, creating a transportation grid for advanced civilizations. Ancient astronomers could have mapped these highways and planned interstellar journeys accordingly. X-ray observations reveal temperature gradients along the tunnel walls, where hot plasma meets cooler surrounding material. These boundary layers create complex fluid dynamics with turbulence and mixing zones. The tunnels remain stable for millions of years, despite ongoing evolution. The discovery changes our understanding of the interstellar medium, from static emptiness to dynamic architecture. Space between stars churns, with ongoing processes driven by stellar evolution. The galaxy operates more like a living organism than a collection of isolated objects. Future space missions could use these plasma channels as natural highways between star systems. The reduced particle density would allow higher velocities with less radiation shielding. Interstellar travel becomes more feasible when you have cosmic infrastructure already in place. Yet the most extraordinary tunnel leads to our nearest stellar neighbors, offering possibilities that science fiction barely imagined. A direct tunnel of superheated gas connects our solar system to Alpha Centauri, creating the first discovered interstellar highway. You always assumed the 4 light-year journey to our nearest stellar neighbors required crossing empty space filled with cosmic dust and radiation. The reality is far more incredible than anyone predicted. The Centaurus tunnel extends from the local hot bubble toward the Alpha Centauri system in a nearly straight line. This plasma channel maintains consistent properties across light-years of distance, like a cosmic fiber optic cable made of million-degree gas. The tunnel walls show remarkable stability, despite the violent forces that created them. X-ray telescopes reveal the highway structure in exquisite detail. The central channel measures roughly 50 light-years in diameter, wide enough to accommodate entire solar systems. Temperature readings show the tunnel interior averages 1.4 million Kelvin, hot enough to strip electrons from atoms instantly. The plasma highway formed when multiple supernova explosions occurred in sequence between our region and Alpha Centauri. Picture dominoes falling in a line, each stellar explosion triggering shockwaves that carved deeper into the tunnel structure. The process required precise timing over millions of years. Alpha Centauri sits at the tunnel's far end, like a lighthouse marking a cosmic harbor. The triple star system consists of Alpha Centauri A, a sun-like yellow star, Alpha Centauri B, an orange dwarf companion, and Proxima Centauri, a red dwarf that hosts potentially habitable planets. The highway reduces travel time for hypothetical spacecraft in unexpected ways. While the tunnel does not shorten physical distance, the low particle density allows much higher velocities. Interstellar ramjet concepts could scoop plasma directly from the tunnel for propulsion fuel. Scientists calculate that spacecraft could achieve 10% light speed through the Centaurus tunnel with current theoretical technology. The journey time drops from 40,000 years using conventional rockets to just 40 years for plasma-powered vessels. Advanced civilizations could traverse the highway in decades rather than millennia. The tunnel also provides natural shielding from cosmic radiation. Dense plasma walls deflect high-energy particles that normally bombard spacecraft during interstellar flight. The magnetic fields embedded in the tunnel structure create protective barriers similar to planetary magnetospheres. Temperature measurements reveal fascinating dynamics within the plasma highway. Hot gas flows toward Alpha Centauri at hundreds of miles per second, creating a cosmic wind that could assist outbound missions. Return journeys would fight against this plasma current, but benefit from reduced particle density. The discovery suggests that similar tunnels connect other nearby star systems. The local galactic arm may contain an entire network of plasma highways left behind by ancient supernova chains. Future surveys with advanced X-ray telescopes could map this interstellar infrastructure. Proxima Centauri b, the potentially habitable planet orbiting our nearest red dwarf neighbor, becomes more accessible through the tunnel route. This rocky world receives stellar radiation levels similar to Earth and may harbor liquid water oceans. The plasma highway transforms Proxima from an impossible destination to a challenging but achievable goal. The tunnel's existence implies that advanced extraterrestrial civilizations already know about these cosmic highways. Any species developing interstellar travel capabilities would discover the plasma channels through X-ray astronomy. They might be using the tunnel network right now. Communications through the Centaurus tunnel could also benefit from plasma wave propagation. Radio signals might travel faster through the ionized medium than through normal space. The tunnel could serve as a natural waveguide for interstellar messaging. However, the plasma highway represents just one thread in a vast network of cosmic infrastructure that dwarfs anything humans have imagined. Rivers of plasma hotter than stellar cores flow between star systems, creating a galactic transportation network that spans thousands of light years. You picture space as cold and empty, a vacuum that spacecraft must struggle through. The truth reveals space as a churning ocean of superheated gas organized into vast currents that dwarf any earthly river system. These cosmic expressways carry temperatures reaching 2 million Kelvin, 20 times hotter than the sun's surface. The plasma flows move at hundreds of miles per second, creating stellar winds that could power entire civilizations. Magnetic fields embedded in the gas streams generate forces equivalent to billions of nuclear power plants. The Expressway system emerged from the most violent events in galactic history. Supernova explosions pump enormous amounts of energy into the interstellar medium, creating blast waves that propagate for millions of years. These shock waves heat surrounding gas to extreme temperatures and set it in motion along predictable paths. Think of the cosmic expressways as celestial arteries, carrying the lifeblood of star formation throughout the galaxy. Hot plasma flows transport heavy elements created in stellar cores to regions where new stars will form. Carbon, oxygen, iron, and other materials essential for rocky planets surf these cosmic currents between stellar nurseries. Scientists map the expressway network using X-ray observatories that detect thermal emission from the superheated gas. The plasma glows like neon signs marking interstellar highways visible from thousands of light years away. Advanced alien civilizations could navigate by these cosmic landmarks just as ancient mariners used stars. The local hot bubble sits at a major expressway intersection, explaining why our region shows such complex structure. Multiple plasma flows converge near the solar system before branching toward different galactic destinations. We live at a cosmic traffic hub that connects dozens of stellar neighborhoods. Plasma velocities within the expressways reach 300 miles per second, fast enough to cross the entire solar system in 1 week. Spacecraft could ride these currents like sailing ships using trade winds, achieving interstellar speeds impossible with conventional propulsion. The key lies in understanding plasma physics and magnetic field interactions. The expressway walls show remarkable organization despite the chaotic forces that created them. Temperature gradients create distinct layers where hot central plasma meets cooler surrounding material. These boundary zones generate turbulence and mixing that enriches the interstellar medium with processed stellar materials. Magnetic fields thread through the plasma flows like invisible railroad tracks, guiding charged particles along specific trajectories. These field lines extend for light years without breaking, creating cosmic infrastructure that could channel spacecraft navigation systems or interstellar communications. The expressways also influence galactic weather patterns by transporting energy between regions of active star formation. Hot plasma from stellar nurseries flows toward cooler areas, equalizing temperatures across vast volumes of space. This cosmic climate control affects where and when new stars can form. Recent discoveries reveal that the Expressway network connects to similar structures in neighboring galaxies. The local group of galaxies shows evidence for intergalactic plasma bridges that span millions of light years. The cosmic highway system may extend throughout the observable universe. Future space missions could map these plasma expressways in detail, revealing optimal routes for interstellar exploration. Just as ancient traders followed river systems to reach distant lands, spacefaring civilizations could use cosmic currents to traverse the galaxy efficiently. The expressway system operates continuously, refreshed by ongoing stellar explosions and powered by galactic rotation. Unlike human-built infrastructure that requires maintenance, these cosmic highways are self-sustaining and grow stronger with time as more supernovas add energy to the network. Yet, all these vast plasma rivers flow through an even larger structure that cocoons our entire solar system in ways we are just beginning to understand. We live inside a giant soap bubble made of million-degree gas that extends farther than most people can imagine. You think our solar system floats freely through empty space between distant stars. The reality is that we exist within a vast cavity carved by ancient explosions, surrounded by walls of superheated plasma that stretch 300 light-years in every direction. The local hot bubble formed between 10 and 20 million years ago, when massive stars in our cosmic neighborhood exploded one after another. These supernova blasts cleared out a spherical cavity in the interstellar medium, like underground explosions, creating a cave system. The shockwaves pushed dense gas away from our region, leaving behind a hollow space filled with extremely hot, thin plasma. Inside the bubble, gas density drops to roughly 1/10 of typical interstellar values. This low-density environment reduces radiation exposure for any spacecraft traveling between nearby stars. The bubble also blocks cosmic rays from distant galactic sources, creating a partially shielded zone around our solar system. Temperature measurements reveal the bubble interior averages 1.2 million Kelvin. This seems incredibly hot, but the gas is so thin that a human body would freeze instantly, despite the high temperature. Think of the difference between a campfire and a blast furnace. Both produce heat, but the campfire contains more total thermal energy because it has more fuel. The local hot bubble contains roughly 500 stars within its boundaries, including many of the bright stars visible in Earth's night sky. Sirius, Procyon, Altair, and other familiar stellar names shine from within our cosmic neighborhood. These stars appear prominently because we see them through the bubble's clear interior rather than dust-obscured external regions. Scientists discovered the bubble's asymmetric shape using the E-Rosetta X-ray telescope. Rather than forming a perfect sphere, the cavity shows elongated extensions and irregular boundaries. These deformations result from interactions with other nearby supernova remnants and the galaxy's magnetic field structure. The bubble's walls consist of compressed gas heated to temperatures exceeding 2 million Kelvin. These boundary regions glow brightly in X-ray wavelengths, creating a cosmic shell visible to space-based telescopes. The wall thickness varies from 10 to 50 light-years depending on local conditions. Stellar winds from hot stars within the bubble maintain the cavity against gravitational collapse. These winds carry enough energy to prevent the surrounding dense gas from flowing back into the cleared region. The bubble remains stable for tens of millions of years before external forces begin to compress it. The solar system sits slightly off-center within the local hot bubble, closer to the boundary in the direction of the constellation Centaurus. This asymmetric position explains why we see more dust and gas clouds in certain sky directions compared to others. The bubble's edge appears as the visible Milky Way band across our night sky. Recent research suggests the bubble continues expanding slowly as additional stellar explosions add energy to the structure. Young, massive stars within the cavity will eventually explode as supernovas, potentially enlarging the bubble further or creating subsidiary cavities connected to the main volume. The local hot bubble's discovery revolutionizes our understanding of the solar system's galactic environment. Rather than traveling through uniform interstellar space, we inhabit a special region shaped by cosmic violence. This protected zone may have influenced Earth's climate and biological evolution by reducing exposure to harmful radiation. Advanced extraterrestrial civilizations throughout the galaxy probably live within similar bubble structures created by local supernova activity. These cosmic sanctuaries provide ideal conditions for long-term planetary evolution and technological development. Life may concentrate within hot bubbles rather than in the galaxy's denser, more radiation-rich regions. The bubble's eventual fate depends on future stellar explosions and interactions with neighboring supernova remnants. Our cosmic home will evolve and possibly merge with adjacent cavities, creating even larger cleared regions in the interstellar medium. However, while we drift safely within this protective cocoon, elsewhere in the galaxy, a stellar bomb prepares to detonate with the force of billions of nuclear weapons. 3,000 light-years away, a white dwarf star accumulates stolen hydrogen like a cosmic suicide bomber preparing to explode. You scan the constellation Corona Borealis tonight and see nothing unusual among its faint stars. Yet hidden in this celestial crown, an invisible stellar remnant builds toward a thermonuclear blast that will suddenly create Earth's newest naked-eye star. T Coronae Borealis consists of two stars, locked in a deadly orbital dance. The white dwarf primary weighs as much as our Sun, but measures only the size of Earth, creating surface gravity 300,000 times stronger than our planet. Its companion, a bloated red giant star, slowly bleeds material toward the compact monster through gravitational attraction. The mass transfer process resembles a cosmic vampire feeding on its victim. Hydrogen-rich gas flows from the red giant's outer atmosphere toward the white dwarf in a spiraling stream called an accretion disk. This disk glows with temperatures reaching 50,000 Kelvin. As gravitational energy converts to heat through friction, material accumulates on the white dwarf's surface, like snow piling up during a blizzard. However, this stellar snow consists of compressed hydrogen gas, heated to millions of degrees. The white dwarf's crushing gravity compresses the accumulated layer until nuclear fusion conditions develop at the surface. When the hydrogen layer reaches critical thickness, explosive nuclear burning ignites across the entire white dwarf surface simultaneously. This runaway fusion process releases more energy in seconds than our Sun produces in thousands of years. The explosion blasts the accumulated material into space at speeds exceeding 6,000 miles per second. T Coronae Borealis last erupted in 1946, creating a magnitude 2 star visible to naked eyes for several days. Astronomers recorded detailed observations as the new star brightened rapidly, then faded over several weeks. The cycle repeats roughly every 80 years as the white dwarf rebuilds its hydrogen fuel supply. Current observations show all indicators pointing toward imminent eruption. The system has been dimming since March 2023, following the same pattern that preceded the 1946 explosion. Spectroscopic monitoring reveals increased mass transfer rates and expanding accretion disk radius. The upcoming blast will increase T Coronae Borealis brightness by 1,000 times, transforming it from an invisible telescopic object to a star-matching Polaris in apparent magnitude. The explosion will be visible worldwide for naked eye observers, creating apparent stellar formation where none existed before. Professional observatories worldwide prepare for intensive monitoring when the eruption occurs. The James Webb Space Telescope, Hubble Space Telescope, and ground-based facilities plan coordinated observations across all wavelengths. This represents the first recurrent nova explosion observable with modern space-based instruments. The nova explosion will eject roughly 1/10,000th of the white dwarf's mass into surrounding space. This material, enriched with carbon, oxygen, and other heavy elements created during the fusion blast, will contribute to the interstellar medium and future star formation processes. Timing predictions focus on late 2025, with some models suggesting November 10 as the most likely eruption date. However, stellar explosions follow complex physics that makes precise prediction impossible. The blast could occur any night within the next few years. The recurrent nova phenomenon demonstrates how white dwarf stars can repeatedly explode without destroying themselves. Unlike type Ia supernovas, where the white dwarf completely detonates, recurrent novas blow off only surface layers, while leaving the compact core intact for future cycles. T Coronae Borealis belongs to a rare class of only 10 known recurrent novae in the entire galaxy. These systems require precisely balanced conditions where mass transfer rates match nuclear burning timescales. Too little material produces no explosion, while too much triggers complete destruction. The upcoming eruption offers unprecedented opportunities to study stellar nuclear physics in real time. Modern instruments can observe the explosion's development from initial ignition through material ejection and subsequent cooling. These observations will refine models of nuclear burning on stellar surfaces. Yet, even this controlled stellar explosion seems gentle compared to the rogue celestial objects that drift alone through the cosmic wilderness between stars. One night this year or next, you will witness something no human has seen in nearly 80 years. A completely new star will suddenly blaze to life in the constellation Corona Borealis, bright enough to see without telescopes or binoculars. This stellar birth happens not from gas and dust forming a new sun, but from an explosive event so violent it outshines entire galaxies. The new star will appear between the bright stars Arcturus and Vega, creating a distinctive arc pattern that ancient astronomers called the Northern Crown. You can find Corona Borealis by looking northeast on summer evenings, where 7 stars form a semicircular crown shape. The new arrival will join this cosmic jewelry as the constellation's second brightest member. When T Coronae Borealis erupts, the light show begins within hours. The invisible 10th magnitude star will brighten rapidly, gaining luminosity faster than any supernova. Within days, it reaches magnitude 2, matching the brightness of Polaris. The apparent stellar creation will be visible worldwide for about 1 week to naked eyes. Professional astronomers call this phenomenon a recurrent nova, but the name understates the drama involved. The explosion releases 10 billion times more energy than the most powerful nuclear weapons ever built. If you could bottle the energy from 1 second of the blast, it would power human civilization for millions of years. The eruption creates spectacular visual effects as ejected material expands into space. High-speed cameras will capture the explosion's development, showing shells of glowing gas expanding at 6,000 miles per second. These ejecta form intricate patterns as they interact with previously expelled material from earlier eruptions. Spectroscopic observations will reveal the explosion's chemical signature as different elements produce characteristic colors. Hydrogen burns with deep red light, oxygen glows green and blue, while carbon appears in ultraviolet wavelengths. The nova becomes a cosmic laboratory for studying nuclear physics under extreme conditions. The new star's brightness will fluctuate dramatically during the first few weeks after eruption. Initial observations show rapid brightening, followed by irregular variations as the blast wave propagates through surrounding material. Multiple peaks and valleys create a complex light curve, unlike steady stellar behavior. Amateur astronomers worldwide will contribute valuable observations using simple equipment. Digital cameras and basic telescopes can track the nova's brightness changes and color evolution. Citizen science projects will coordinate thousands of measurements from observers across different time zones. The explosion will be visible from every continent except Antarctica during local nighttime hours. Southern Hemisphere observers see Corona Borealis low on the northern horizon, while northern observers enjoy the constellation high overhead. Light pollution in major cities will dim the view but cannot hide such a bright stellar event. Space-based telescopes will observe wavelengths invisible from Earth's surface. The Hubble Space Telescope will capture ultraviolet light from the explosion's hottest regions. The James Webb Space Telescope will peer through dust clouds using infrared detectors. X-ray observatories will monitor the blast's most energetic emissions. The nova's appearance will trigger intense media coverage as news outlets report the sudden stellar creation. Social media will explode with amateur photographs and time-lapse videos showing the new star's emergence. This becomes the first major astronomical event of the smartphone era, visible without special equipment. Education systems worldwide will use the nova as a teaching opportunity to explain stellar evolution and nuclear physics. Students can observe ongoing astrophysical processes rather than studying static textbook illustrations. The explosion demonstrates cosmic violence on scales that dwarf earthly experience. The new star will gradually fade over several months as ejected material expands and cools. By the following year, T Coronae Borealis returns to invisibility, leaving only faint nebular remnants detectable with powerful telescopes. The next eruption will occur roughly 80 years later, when today's children reach old age. However, this controlled stellar explosion represents only one type of cosmic violence among the many forms of destruction that white dwarf stars can unleash. The most common stellar remnants in our galaxy operate as cosmic time bombs, waiting for the right conditions to detonate. You see white dwarf stars as peaceful points of light, slowly cooling over billions of years. The reality is far more explosive. These stellar corpses can trigger nuclear blasts that rival the most violent events in the universe. White dwarf stars form when sun-like stars exhaust their nuclear fuel and shed their outer layers. The remaining core collapses under its own gravity until electron pressure halts further compression. The result is a stellar remnant with the mass of our Sun, compressed into a sphere the size of Earth. Surface gravity on a white dwarf reaches 300,000 times Earth's pull. A sugar cube would weigh as much as a car on such a world. This crushing gravitational field creates the conditions necessary for explosive nuclear burning when fresh fuel becomes available. Most white dwarfs exist in binary systems where they orbit companion stars. When the companion expands during its own stellar evolution, material begins flowing toward the white dwarf through gravitational attraction. This process transforms peaceful stellar remnants into potential superweapons. The transferred material accumulates on the white dwarf's surface in a thin layer that grows denser over thousands of years. Temperature and pressure increase gradually until nuclear fusion conditions develop. Unlike controlled burning in stellar cores, fusion on white dwarf surfaces proceeds explosively once ignited. Nova explosions occur when accumulated hydrogen ignites in runaway nuclear reactions. The blast consumes the entire surface layer within hours, ejecting material at thousands of miles per second. Energy release exceeds 10 billion nuclear weapons, detonating simultaneously across the white dwarf's surface. Some white dwarfs trigger even more catastrophic explosions, called Type Ia supernovas. When accumulated material pushes the white dwarf's mass past 1.4 solar masses, the entire star detonates in a thermonuclear blast visible across billions of light-years. Nothing remains except expanding debris clouds enriched with heavy elements. The galaxy contains roughly 10 billion white dwarf stars, making them the most numerous stellar remnants. About half exist in binary systems capable of mass transfer events. This means 5 billion potential nova or supernova sources lurk throughout the Milky Way, waiting for the right trigger conditions. Nova explosions occur roughly once per year somewhere in our galaxy. Most happen too far away or behind dust clouds to see from Earth. However, historical records document several naked-eye novae that appeared as new stars in familiar constellations before fading away. The most famous white dwarf bomb sits in the constellation Cygnus, where a stellar remnant named WD 1933 plus 229 slowly accumulates helium from its companion star. Astronomers predict this system will explode as a Type Ia supernova within 100 million years, creating a blast visible in daylight. White dwarf explosions contribute essential heavy elements to galactic chemical evolution. Iron, nickel, chromium, and other metals forged in thermonuclear blasts seed the interstellar medium for future star and planet formation. Every atom in your body heavier than oxygen was likely created in white dwarf explosions. The discovery of white dwarf variability revolutionized understanding of stellar evolution endpoints. Rather than simply cooling and fading, these stellar remnants remain active participants in galactic processes through explosive interactions with companion stars. Advanced civilizations orbiting white dwarf systems would face periodic extinction events from nova explosions. The blast radiation would sterilize planets within several astronomical units and disrupt atmospheric chemistry across entire solar systems. Survival requires either deep underground shelters or interplanetary evacuation. Future space missions could observe white dwarf systems before, during, and after explosive events. Real-time monitoring would reveal the detailed physics of thermonuclear burning under extreme conditions impossible to reproduce in terrestrial laboratories. Yet while white dwarf explosions represent the most common stellar violence, the systems that create them showcase even more dramatic examples of cosmic destruction through gravitational warfare. Two stars locked in orbital combat generate the most spectacular explosions known to astronomy. You imagine binary star systems as peaceful cosmic couples dancing through space together. The truth reveals gravitational warfare that tears stars apart, triggers nuclear detonations, and creates some of the most luminous events in the observable universe. Closed binary systems experience tidal forces that distort both stellar companions into egg-shaped objects. The gravitational pull stretches each star toward its partner, creating bulges that point toward the orbital center. These deformations cause the stellar surfaces to heat up through internal friction, making binary stars brighter and more active than single stars. When one star evolves faster than its companion, the binary system becomes a cosmic vampire. The more massive star expands into a red giant first, filling its gravitational influence zone, called the Roche lobe. Material from the bloated giant flows toward its compact companion through the gravitational balance point between the two stars. This mass transfer creates spectacular accretion disks around the receiving star. Picture a cosmic whirlpool where stolen stellar material spirals inward at tremendous velocities. Friction heats the disk until it glows brighter than many entire galaxies, creating some of the most luminous objects in the universe. The most extreme binary systems contain a black hole or neutron star paired with a normal stellar companion. These high-mass compact objects strip material from their partners with devastating efficiency, gas falling toward the compact object accelerates to significant fractions of light speed, generating X-ray emission visible across galactic distances. Cataclysmic variables represent binary systems where a white dwarf strips hydrogen from a main sequence companion. The accumulated material builds up on the white dwarf's surface until explosive nuclear burning ignites. These nova explosions can repeat every few decades or centuries, creating recurrent stellar bombs. Some binary systems experience contact phases, where both stellar surfaces actually touch. The two stars share a common atmospheric envelope, while their cores remain distinct. These contact binaries often merge completely, triggering luminous red nova explosions that can outshine their host galaxies temporarily. X-ray binary systems produce jets of material moving at nearly light speed. These relativistic outflows extend for light years from the central binary, creating cosmic blowtorches that heat surrounding gas to temperatures exceeding 1 billion degrees. The jets rival quasar emissions, despite originating from stellar mass objects. Wolf-Rayet binary systems showcase the most violent stellar winds known to astronomy. These hot, massive stars lose material at rates millions of times greater than our sun's solar wind. When paired with compact companions, the interaction creates complex shock structures and particle acceleration zones. Symbiotic stars demonstrate long-term binary evolution, where a white dwarf slowly accretes material from a red giant companion over millions of years. These systems undergo periodic outbursts as accumulated material reaches critical densities for explosive nuclear burning. The cycle can repeat hundreds of times during the binary's lifetime. Type Ia supernovas, the thermonuclear explosions that destroy white dwarf stars, occur exclusively in binary systems. The white dwarf must accrete enough material from its companion to exceed the critical mass limit. These explosions serve as standard candles for measuring cosmic distances and discovering dark energy. Gravitational wave observatories detect binary neutron star mergers that create kilonovas, explosive events that forge heavy elements like gold and platinum. These cosmic collisions occur when two ultra-dense stellar remnants spiral inward and merge in cataclysmic explosions, visible across billions of light years. The galaxy contains millions of interacting binary systems at various evolutionary stages. Each represents a potential future explosion, as gravitational forces drive the stellar components toward increasingly violent interactions. Binary evolution timescales ensure continuous fireworks throughout galactic history. Advanced alien civilizations in binary star systems would experience regular cosmic disasters from their host stars' violent interactions. Planetary survival requires either advanced technology to deflect stellar emissions or migration to more stable single-star systems. However, even these spectacular binary explosions seem tame compared to the solitary wanderers that drift through interstellar space without any stellar companions at all. Billions of worlds wander the galaxy in eternal darkness, ejected from their birth systems to roam between the stars forever. You picture planets as objects that orbit stars, warmed by stellar radiation and locked in stable solar systems. However, gravitational chaos during planetary formation flings countless worlds into the cosmic wilderness, where they drift alone through space, colder than Antarctica. These rogue planets outnumber star-bound worlds by astronomical margins. Computer simulations suggest that for every planet orbiting a star, 10 others float freely through interstellar space. The Milky Way contains roughly 400 billion rogue planets, creating a hidden population of dark worlds that vastly exceeds the number of stars. Most rogue planets form around stars like normal worlds, but get ejected during chaotic early phases of solar system evolution. When multiple giant planets orbit close to each other, gravitational interactions eventually destabilize the configuration. The unlucky planet receives a gravitational slingshot that accelerates it beyond the star's escape velocity. Some rogue planets form directly from collapsing gas clouds without ever belonging to stellar systems. These cosmic orphans develop like failed stars that lack sufficient mass to ignite nuclear fusion. They burn briefly from gravitational contraction heat, then fade into darkness as they cool over billions of years. The closest rogue planet to Earth likely sits within 12 light-years of our solar system. This invisible world drifts through space at typical velocities of 20 miles per second, crossing distances equivalent to Earth's orbit every few months. We could discover it any day through advanced infrared telescopes or gravitational microlensing surveys. Surface conditions on rogue planets rival the most extreme environments imaginable. Without stellar heating, atmospheric temperatures plummet to near absolute zero. Any oceans freeze solid within millions of years after ejection. The worlds become cosmic icebergs covered in frozen nitrogen, oxygen, and other atmospheric gases. However, some rogue planets might harbor life in subsurface oceans, heated by radioactive decay or tidal forces from massive moons. Jupiter's moon, Europa, demonstrates how gravitational flexing can maintain liquid water beneath ice shelves. Rogue planets with similar moons could preserve habitable environments for billions of years. The James Webb Space Telescope recently discovered 6 new rogue brown dwarfs, objects intermediate between giant planets and failed stars. These cosmic vagabonds generate their own heat through nuclear fusion of deuterium, creating faint infrared signatures detectable across interstellar distances. One discovered rogue object, designated SIMP, displays remarkable properties despite its solitary existence. This failed star generates magnetic fields 200 times stronger than Jupiter's, powerful enough to accelerate charged particles and create spectacular aurora displays in the interstellar medium. Rogue planets occasionally pass through occupied solar systems, creating temporary gravitational disruption before continuing their lonely journeys. Such encounters could destabilize asteroid belts, perturb comet clouds, or even capture the wandering world as a new member of the host system. Advanced spacefaring civilizations might colonize rogue planets as mobile bases for interstellar exploration. These worlds offer gravitational anchors and potential resources while traveling between star systems. Underground colonies could exploit geothermal energy and create artificial ecosystems independent of stellar radiation. Some rogue planets retain large moons ejected alongside their primary world. These binary planetary systems drift through space together, maintaining orbital relationships that could preserve tidal heating and atmospheric dynamics. Double planets might offer better prospects for sustaining life than solitary rogues. Future surveys will discover thousands of rogue planets using gravitational microlensing techniques. When a rogue world passes between Earth and a background star, its gravity focuses starlight like a natural lens. These temporary brightening events reveal the invisible planet's presence and mass. The abundance of rogue planets suggests that planetary formation processes are far more violent and chaotic than previously understood. Most worlds experience ejection events during their early history, with only the fortunate few remaining in stable orbits around their birth stars. Yet, while rogue planets drift silently through cosmic darkness, other failed stars blaze with spectacular displays that rival the Aurora Borealis on cosmic scales. In the depths of interstellar space, failed stars create light shows that dwarf Earth's northern lights by millions of times. You associate auroras with planetary magnetospheres interacting with stellar winds from nearby suns. However, brown dwarf stars generate their own particle beams and magnetic fields powerful enough to create cosmic aurora displays visible across light years of distance. Brown dwarfs occupy the borderland between giant planets and true stars, with masses ranging from 13 to 80 times Jupiter's weight. These objects ignite deuterium fusion reactions that provide modest energy output for millions of years. However, they lack sufficient mass to sustain hydrogen burning like normal stars. SIMP represents the most spectacular example of a brown dwarf light show discovered to date. This failed star generates magnetic fields 200 times stronger than Jupiter's, creating a cosmic dynamo that accelerates charged particles to incredible energies. The resulting aurora emissions shine brightly in radio wavelengths detectable from Earth. The brown dwarf's magnetic field extends millions of miles into surrounding space, creating a vast magnetosphere larger than many stellar systems. Charged particles trapped within this magnetic prison spiral along field lines at near light speeds, generating radio emissions through a process called synchrotron radiation. Unlike planetary auroras that require external energy sources like stellar winds, brown dwarf light shows are completely self-sustaining. The failed star's own rotation and convection patterns generate the magnetic fields that trap and accelerate particles. This creates perpetual aurora displays that continue for millions of years without external input. The radio emissions from brown dwarf auroras can be detected using ground-based telescopes across interstellar distances. These signals provide valuable information about magnetic field strength, rotation rates, and atmospheric dynamics on objects too faint to study through conventional optical astronomy. Some brown dwarfs show periodic variations in their radio emissions, suggesting that their aurora displays rotate in and out of view like cosmic lighthouses. The rotation periods range from 2 to 20 hours, much faster than typical stellar rotation rates. This rapid spin enhances the magnetic dynamo effect that powers the aurora emissions. Temperature differences between brown dwarf poles and equators create complex atmospheric circulation patterns that influence aurora activity. Hot gases rise at the equator and sink at the poles, creating convection cells that interact with magnetic fields. This process generates variable aurora emissions that change over time, scales of hours to days. Binary brown dwarf systems create even more spectacular aurora displays when magnetic fields from both objects interact. The combined magnetospheres generate shock structures and particle acceleration zones that produce radio emissions detectable across hundreds of light years. These double light shows rival emissions from much more massive stellar objects. Recent discoveries reveal brown dwarf auroras extend beyond radio wavelengths into optical and X-ray emissions. The most energetic particles generate high-frequency radiation when they collide with atmospheric gases. These multi-wavelength aurora displays provide detailed information about brown dwarf atmospheric composition and magnetic field structure. The abundance of brown dwarfs throughout the galaxy means that interstellar space contains millions of these cosmic light shows. Advanced alien civilizations might navigate by brown dwarf radio beacons, using their periodic signals as natural navigation aids for interstellar travel. Brown dwarf auroras also influence nearby space environments by generating high-energy particle beams that extend far beyond their immediate magnetospheres. These particle streams could affect the evolution of surrounding dust clouds and provide energy sources for exotic chemical reactions in the interstellar medium. Future radio telescope arrays will map brown dwarf aurora emissions throughout the local galactic neighborhood. This survey will reveal the three-dimensional structure of failed star magnetic fields and provide insights into dynamo processes operating under conditions impossible to replicate in terrestrial laboratories. The discovery that isolated brown dwarfs can generate spectacular light shows demonstrates how magnetic field interactions create cosmic phenomena far removed from stellar heating and planetary dynamics. The universe contains many more sources of electromagnetic displays than astronomers previously recognized. However, these solitary light shows pale compared to the drama unfolding as actual stars barrel toward our solar system on collision courses that will reshape the night sky. Right now, dozens of stars race through space on trajectories that will bring them dangerously close to our solar system within the next few million years. You assume the stellar neighborhood remains stable, with fixed constellation patterns that persist throughout human history. However, stars move through the galaxy at tremendous velocities, and several are heading directly toward us on cosmic collision courses. Gaia Space Telescope data reveals the three-dimensional motions of millions of nearby stars with unprecedented precision. By tracing their paths backward and forward in time, astronomers identify stellar encounters that occurred in the distant past and predict future close approaches. The results show that our galactic neighborhood experiences regular traffic from wandering stars. HIP 85605, currently located 240 light-years away in the constellation Hercules, will approach within 16 light-years of the Sun in approximately 240,000 years. This K-type orange star will become visible to naked eyes as it brightens during the encounter, potentially reaching 4th magnitude. Gliese 710 leads the parade of approaching stars with its dramatic encounter planned for 1.3 million years from now. This orange dwarf will pass closer than any star in recorded galactic history, coming within just 10 trillion miles of our solar system. The visitor will outshine every current star and remain visible as a bright orange disk for thousands of years. Ross 128, a red dwarf star currently invisible to naked eyes, will pass within 9 light-years in roughly 300,000 years. During closest approach, this faint star will brighten to 6th magnitude, just at the limit of naked eye visibility under dark skies. These stellar encounters trigger cascading effects throughout the solar system's outer regions. The Oort cloud, containing trillions of dormant comets, extends halfway to the nearest stars. Approaching stars will gravitationally disturb these icy bodies, sending showers of comets toward the inner planets for millions of years following each encounter. Computer models predict that major stellar encounters increase comet impact rates on Earth by factors of 10 to 100. The late heavy bombardment that scarred the Moon 4 billion years ago may have resulted from a similar stellar flyby that disrupted the early solar system's comet populations. Stellar velocities relative to the Sun range from 10 to 100 miles per second, fast enough to cross the entire solar system in just a few years. These high-speed encounters create brief but intense gravitational perturbations that can alter planetary orbits and destabilize asteroid trajectories. The closest historical stellar encounter occurred roughly 70,000 years ago, when Schultz's star, a red dwarf, brown dwarf binary system, passed within 1 light-year of the Sun. This close approach likely triggered a minor comet shower that early humans might have observed as increased meteor activity. HIP 89825 will approach within 28 light-years in approximately 400,000 years. This G-type star, similar to our Sun, could become bright enough to see without optical aid, temporarily joining the roster of prominent naked-eye stars. Future stellar encounters will reshape Earth's night sky as approaching stars grow brighter while receding stars fade into invisibility. Constellation patterns will evolve dramatically over geological timescales, creating completely different star maps for future civilizations to study. Advanced warning of stellar encounters provides opportunities for defensive measures against increased comet bombardment. Space-based survey systems could track approaching objects and deploy deflection technologies to protect Earth from impact threats triggered by stellar flybys. The regular passage of wandering stars through our cosmic neighborhood demonstrates that the solar system exists within a dynamic galactic environment. Rather than drifting through empty space in isolation, we participate in ongoing stellar interactions that influence planetary evolution and space weather patterns. These approaching visible stars represent only the tip of the cosmic iceberg, because even darker and more dangerous objects prowl through our galactic neighborhood completely invisible until they reveal themselves through gravitational effects. The most dramatic transformation in Earth's night sky begins in roughly 1.3 million years, when an unremarkable orange star evolves into the brightest celestial object. Except for the Sun and Moon, you can barely detect Gliese 710 with powerful telescopes today, a faint 9th magnitude speck lost among thousands of similar dim stars. This cosmic sleeper will soon rewrite every astronomy textbook as it approaches our solar system. The approaching orange dwarf currently creeps toward us at 43,000 miles per hour, from 63.8 light-years away. Think of a distant headlight growing brighter as a car approaches on a dark highway. Gliese 710 follows a similar path through 3-dimensional space, heading directly for our cosmic neighborhood. When the encounter begins, the star will brighten night by night like a slow-motion fireworks display. Amateur astronomers will track its steady increase from invisibility to naked eye visibility. Professional observatories will monitor every detail as Gliese 710 transforms from a telescopic curiosity into the most prominent star in Earth's sky. The orange visitor will peak at magnitude -2.7, matching Jupiter's maximum brightness and outshining Sirius by 4 times. Unlike every other star you see as a point of light, Gliese 710 will appear as an actual visible disk. Advanced telescopes will resolve surface features on this approaching stellar neighbor. The star will become 140,000 times brighter than today, creating the most spectacular stellar brightening event in human memory. Ancient civilizations recorded supernovas that appeared as new stars, but those explosions lasted only weeks or months. Gliese 710 will dominate the night sky for nearly 20,000 years. During closest approach, the orange star will pass within 0.166 light-years of our solar system, roughly 10 trillion miles away. This distance seems vast by earthly standards, but represents extremely close quarters in galactic terms. The encounter qualifies as the nearest stellar flyby in millions of years. Skywatchers will observe the star's motion against background constellations, drifting visibly at nearly 1 arc-minute per year. This angular velocity equals the apparent diameter of Jupiter, allowing dedicated observers to track the star's movement over human lifetimes. Future generations will inherit completely different constellation patterns. The approaching star measures slightly smaller than our Sun, with roughly 60% solar mass and a surface temperature of 4,000 Kelvin. This K7V classification indicates a stable, long-lived star that burns hydrogen steadily without dramatic variability. Gliese 710 poses no radiation threat despite its eventual brightness. Spectroscopic analysis reveals the star's composition includes heavy elements created in previous generations of stellar nucleosynthesis. Iron, carbon, oxygen, and other metals appear in absorption lines that provide detailed information about the star's internal structure and evolutionary history. The orange star's approach will trigger intense scientific interest as astronomers study stellar properties with unprecedented detail. Ground-based telescopes will resolve the star's disk and potentially detect sunspots or other surface features. Space-based observatories will monitor across all wavelengths from radio to gamma rays. However, this approaching bright star brings dangers that extend far beyond pretty light shows, as its gravity prepares to unleash cosmic destruction on a scale that dwarfs any natural disaster in Earth's history. A spherical shell of trillions of frozen bodies surrounds our solar system like a cosmic minefield, waiting for the right trigger to explode into chaos. You picture the space beyond Pluto as empty darkness extending toward distant stars. The reality reveals a vast arsenal of icy projectiles that gravitational encounters can transform into weapons of planetary destruction. The Oort cloud extends from roughly 20,000 to 100,000 astronomical units from the Sun, creating a spherical boundary that marks our solar system's true edge. This cosmic deep freeze contains an estimated 1 trillion comet nuclei, each representing a potential impact threat if disturbed by passing stars. These ancient remnants from solar system formation orbit at velocities measured in yards per second, barely moving relative to the distant Sun. The icy bodies follow highly elliptical paths that take millions of years to complete. Most have remained undisturbed since the planets finished forming 4.5 billion years ago. When Gliese 710 barrels through this cosmic shooting gallery, its gravity will act like a pinball machine flipper, launching projectiles in every direction. Computer simulations show that the stellar encounter will scatter roughly 10% of all Oort cloud objects into new trajectories that cross planetary orbits. The gravitational disruption process works through 3 body dynamics involving the Sun, approaching star, and individual comet nuclei. As Gliese 710 passes through the outer solar system, its gravity competes with solar attraction for control over comet orbits. Objects caught between these competing forces receive gravitational kicks that send them flying. Some comets will gain enough energy to escape the solar system entirely, ejected into interstellar space to become rogue objects drifting between stars. Others will fall toward the inner planets on collision courses that take thousands of years to complete. The most dangerous outcomes involve comets deflected into Earth-crossing orbits. The approaching star will pass closest to the Oort cloud's densest regions, maximizing gravitational disruption effects. Peak disturbance occurs when Gliese 710 reaches perihelion at 0.166 light-years from our solar system. The encounter duration spans roughly 50,000 years as the star approaches, passes, and recedes. Mathematical models predict that comet bombardment rates will increase by factors of 10 to 100 following the stellar encounter. Instead of seeing a few bright comets per decade, future skywatchers might observe dozens annually for millions of years. The night sky will transform into a cosmic fireworks display. Long-period comets take thousands of years to travel from the Oort cloud to the inner solar system. This delay means that increased bombardment begins roughly 1 million years after Gliese 710's closest approach. Future civilizations will experience the consequences of today's approaching stellar encounter. The disrupted comets will approach from all directions rather than following the ecliptic plane where planets orbit. This spherical distribution makes defense more challenging, since impacts could occur from any angle. Traditional planetary protection strategies assume threats arrive from predictable directions. Historical precedents show that major stellar encounters correlate with mass extinction events in Earth's fossil record. The Ordovician extinction 450 million years ago coincided with evidence for increased comet bombardment. Similar patterns appear at other extinction boundaries. Advanced spacefaring civilizations will need comprehensive comet deflection systems to survive prolonged bombardment periods. Nuclear pulse propulsion, gravity tractors, or kinetic impactors could redirect threatening objects. However, the sheer number of incoming comets will strain any defensive network. The Oort cloud disruption will also affect other solar system bodies through gravitational perturbations and collisional cascades. Asteroid belt dynamics could change as scattered objects pass through inner planetary regions. Even the giant planets might experience orbital modifications from accumulated gravitational tugs. Yet, the scale of this coming comet catastrophe represents just the opening act in a bombardment scenario that will transform the inner solar system into a cosmic war zone for millions of years. The most prolonged natural disaster in Earth's future will unfold over millions of years as an endless stream of icy projectiles rain down from the outer solar system. You imagine comet impacts as rare events that occur once per century or millennium. However, stellar encounters can trigger cascading bombardments that make the asteroid impact that killed the dinosaurs seem like a gentle shower. Computer models predict that roughly 10 comets annually will cross Earth's orbit during peak bombardment periods following the Gliese 710 encounter. This represents a 100-fold increase over current impact rates. Instead of major impacts every few million years, Earth faces potential collisions every few thousand years for extended periods. Each incoming comet carries kinetic energy equivalent to millions of nuclear weapons. A typical 1-mile diameter comet nucleus, traveling at cosmic velocities, delivers explosive force comparable to 100 million megatons of TNT. The Chicxulub impact that ended the dinosaur era released roughly the same energy from a 6-mile-wide asteroid. The bombardment will affect every planet in the solar system, not just Earth. Mars, with its thinner atmosphere and weaker gravity, becomes especially vulnerable to surface modification from comet impact. The red planet could experience enough collisions to completely resurface large regions and potentially thicken its atmosphere through impact-released volatiles. Venus will receive its share of comet impacts, adding water and organic compounds to its hellish surface environment. These volatile-rich projectiles might temporarily moderate surface temperatures by increasing atmospheric reflectivity. However, the planet's extreme greenhouse conditions will quickly vaporize any accumulated ice. The gas giant planets face bombardment from scattered Oort cloud objects on highly inclined orbits. Jupiter and Saturn will capture many incoming comets, adding mass to their already substantial bulk. These captured objects will create spectacular atmospheric entries, visible as bright fireballs in the giant planet's thick atmospheres. Comet impacts on airless bodies like the Moon and asteroids will create fresh crater chains and debris clouds that enhance zodiacal light visibility from Earth. The lunar surface will acquire thousands of new impact sites, fundamentally altering its appearance and potentially exposing subsurface materials. The cascading effects extend beyond direct impacts through orbital perturbations and collision fragments. Large comet impacts will excavate substantial amounts of planetary material, ejecting rocks and dust into interplanetary space. These impact ejector clouds will create hazards for spacecraft and potentially trigger secondary impacts on neighboring worlds. Earth's climate system will experience repeated disruptions from major comet impacts that inject dust and vapor into the stratosphere. Each significant collision could trigger impact winters lasting months or years. Multiple impacts within short time periods might cause prolonged climate instability. The biological consequences of sustained comet bombardment include both destruction and evolutionary opportunity. While large impacts threaten mass extinctions, smaller collisions deliver organic compounds and water that could enhance biochemical diversity. Life must adapt to a cosmic environment featuring regular catastrophic events. Future civilizations will need comprehensive planetary defense systems capable of detecting and deflecting multiple simultaneous threats. Early warning networks must track thousands of incoming objects across the entire celestial sphere. Deflection technologies must operate continuously rather than responding to isolated threats. The comet cascade will also provide unprecedented opportunities for scientific study of these primitive solar system remnants. Instead of launching expensive deep space missions to study individual comets, researchers will have access to hundreds of objects passing through the inner solar system. Mining operations could exploit incoming comets as sources of water, organic compounds, and rare isotopes. These icy bodies contain materials largely unchanged since solar system formation, providing valuable resources for space-based industries and life support systems. The bombardment period will eventually end as the Oort cloud reaches a new equilibrium configuration. However, the effects will persist for billions of years through altered planetary surfaces, modified atmospheric compositions, and evolutionary changes in surviving life forms. However, while comets rain down from the solar system's edge, even more dangerous objects prowl through interstellar space completely invisible until they announce themselves through gravitational violence. Invisible predators, weighing as much as dozens of suns, drift silently through our galactic neighborhood, revealing themselves only when they devour unlucky stars or bend light from distant objects. You assume black holes remain safely confined to exotic locations far from inhabited solar systems. The truth is that millions of these cosmic monsters roam freely through the galaxy, including at least one confirmed wanderer already loose in the Milky Way. The first confirmed rogue stellar mass black hole weighs 7.1 solar masses and travels through space at 45 miles per second. This cosmic bullet revealed itself through gravitational microlensing when it passed between Earth and a background star. The black hole's gravity focused starlight like a natural magnifying glass, creating a brightening event that lasted 300 days. Astronomers detected the invisible monster by watching how it distorted light from a star located 25,000 light-years away, near the galactic center. As the black hole drifted across our line of sight, its gravitational field bent and amplified the background star's light according to Einstein's relativity predictions. The wandering black hole currently sits roughly 5,000 light-years from Earth in the constellation Sagittarius. At its current velocity, this cosmic vagrant completes one orbit around the galactic center every 200 million years. It has circled the Milky Way roughly 50 times since forming billions of years ago. Scientists estimate that our galaxy contains roughly 100 million stellar mass black holes, created from massive star explosions throughout galactic history. Most remain invisible because they lack nearby material to consume. These cosmic ghosts drift through space completely undetectable until gravitational effects reveal their presence. The discovery process required 6 years of careful observations using ground-based telescopes and the Hubble Space Telescope. Researchers had to rule out alternative explanations like dim binary star systems or free-floating planets before confirming the black hole interpretation. Statistical analysis suggests that several hundred stellar mass black holes lurk within 100 light-years of our solar system. These local monsters pose minimal direct threat due to their small size and enormous distances. However, a close encounter could gravitationally disrupt planetary orbits or trigger comet showers. Advanced computer simulations reveal that stellar mass black holes occasionally get ejected from binary systems through gravitational slingshot effects. When one star explodes as a supernova, the resulting black hole might receive a velocity kick that exceeds the system's escape speed. The ejected black hole becomes a cosmic nomad, wandering between stars. Some rogue black holes achieve velocities exceeding 1,000 miles per second, fast enough to escape the galaxy entirely. These hypervelocity objects race through intergalactic space as messengers from distant stellar explosions. Future surveys might detect their gravitational signatures as they pass through our cosmic neighborhood. The nearest confirmed black hole to Earth, designated Gaia Black Hole 1, sits just 1,560 light-years away in the constellation Ophiuchus. This 10 solar mass monster orbits a sun-like star every 185 days, but remains completely invisible because it generates no detectable radiation. Breakthrough detection methods now allow astronomers to find black holes through their gravitational effects alone without requiring bright accretion disks or X-ray emissions. This capability revolutionizes black hole astronomy by revealing the dark population that vastly outnumbers actively feeding systems. The galactic black hole census will grow dramatically as space-based telescopes, like the upcoming Nancy Grace Roman Observatory, conduct systematic gravitational microlensing surveys. These missions could discover thousands of previously unknown stellar mass black holes throughout the Milky Way. Future interstellar expeditions must account for invisible black hole hazards when planning trajectories between star systems. Navigation systems will need comprehensive black hole catalogs to avoid gravitational encounters that could destroy spacecraft or strand crews in hostile environments. However, the stellar mass black holes drifting through our galaxy represent just the visible tip of a cosmic iceberg, because gravitational lensing reveals that space hides objects far stranger and more dangerous than anyone imagined. The universe contains hidden populations of dark objects that reveal themselves only when they accidentally focus light from distant sources like cosmic magnifying glasses. You trust that telescopes show you everything important in the night sky through direct observation. However, gravitational lensing exposes invisible monsters that dwarf the number of visible stars and galaxies by enormous margins. Einstein's general relativity predicts that massive objects bend spacetime around themselves, creating curvature that deflects light rays passing nearby. Think of a bowling ball placed on a stretched rubber sheet, creating a depression that marbles roll around. Massive cosmic objects work similarly, creating gravitational wells that focus light into observable brightening events. Microlensing surveys detect these invisible objects when they drift between Earth and background stars. The foreground object's gravity acts as a natural telescope, magnifying the background star's light by factors ranging from 2 to several thousand. The brightening follows a characteristic curve that reveals the hidden object's mass and distance. Current surveys discover roughly 1,000 microlensing events annually, indicating a vast population of dark objects throughout the galaxy. These include brown dwarf stars, too faint to see directly, rogue planets ejected from their birth systems, and stellar mass black holes wandering between stars. The most dramatic microlensing events involve massive objects that create multiple images of background sources. These gravitational mirages appear as Einstein rings, or multiple point sources that shift positions as the lensing object moves. Advanced telescopes can resolve these complex light patterns to determine precise masses and trajectories. Some microlensing events last for years, as extremely massive objects slowly cross our line of sight to distant stars. These long-duration events suggest invisible monsters weighing hundreds or thousands of solar masses drifting through the galactic disk. The nature of these dark behemoths remains mysterious. Free-floating planets represent the most common microlensing discoveries, revealing that rogue worlds outnumber stars throughout the galaxy. These cosmic orphans drift alone through interstellar space after being ejected from their birth systems during chaotic planetary formation processes. Binary black hole systems create especially complex microlensing signatures as both components contribute to light-bending effects. The resulting magnification patterns shift rapidly as the black holes orbit each other, creating unique fingerprints that reveal orbital parameters and individual masses. Primordial black holes formed in the early universe could constitute significant fractions of dark matter if they exist in large numbers. Microlensing provides one of the few methods capable of detecting these ancient remnants from cosmic inflation. However, surveys have not yet confirmed substantial populations of primordial black holes. The upcoming Nancy Grace Roman Space Telescope will revolutionize microlensing astronomy by monitoring hundreds of millions of stars simultaneously. This space-based survey will discover thousands of black holes, rogue planets, and other invisible objects throughout the Milky Way's central regions. Gravitational wave observatories complement microlensing surveys by detecting black hole mergers that create space-time ripples. When two stellar mass black holes spiral together and collide, they generate gravitational waves observable across billions of light years. These events reveal black hole properties impossible to measure through electromagnetic observations alone. Machine learning algorithms now analyze microlensing light curves to classify different types of invisible objects automatically. Artificial intelligence systems can distinguish between planetary signals, stellar remnant signatures, and exotic object candidates among millions of potential events. The dark object census suggests that visible matter represents only a small fraction of the galaxy's total mass budget. Brown dwarfs, rogue planets, stellar remnants, and other invisible components may collectively outweigh all the stars we can see directly. Future gravitational lensing networks will provide early warning systems for dangerous objects approaching inhabited solar systems. By tracking the motions of invisible monsters throughout the galactic neighborhood, astronomers could predict potential encounters centuries or millennia in advance. Yet even these roaming stellar mass monsters pale compared to the supermassive leviathans that can break free from their galactic prisons to become cosmic weapons of unimaginable destruction. The most massive objects in the universe can become cosmic cannonballs blasted out of their home galaxies at millions of miles per hour, carrying enough destructive power to sterilize entire galactic regions. You assume supermassive black holes remain safely anchored at galaxy centers where they formed billions of years ago. However, violent galactic mergers can eject these monsters into intergalactic space as wandering weapons of mass destruction. Supermassive black holes, weighing millions or billions of solar masses, normally sit at galaxy centers like cosmic anchors, their immense gravity binding entire stellar systems together. However, when two galaxies collide and merge, their central black holes eventually spiral toward each other in a deadly gravitational dance that can end in catastrophic ejection. The ejection process begins when two supermassive black holes form a binary system during galactic merger events. These cosmic titans orbit each other while losing energy through gravitational wave radiation. As the orbit shrinks, the black holes approach closer until asymmetric gravitational wave emission during final merger kicks one or both objects out of the galaxy. A 2024 TVD represents the first confirmed supermassive black hole caught in the act of escaping from its host galaxy. This cosmic runaway weighs several million solar masses and currently sits 2,600 light-years from its galaxy's center, traveling at hundreds of miles per second. The ejected monster revealed itself by shredding and consuming a star that wandered too close. The escaped black hole creates a spectacular tidal disruption event as stellar material spirals into its accretion disk. Gas heated to millions of degrees generates brilliant X-ray and optical emissions visible across billions of light-years. These cosmic lighthouses announce the presence of otherwise invisible wandering monsters. Computer simulations show that roughly 10% of supermassive black hole mergers result in at least one object receiving sufficient velocity to escape its host galaxy. The most extreme kicks can accelerate black holes to speeds exceeding 3,000 miles per second, fast enough to traverse entire galaxy groups within billions of years. Ejected supermassive black holes become intergalactic nomads, carrying devastating consequences for any stellar systems they encounter. A wandering black hole passing through a galaxy could gravitationally disrupt star formation regions, scatter stellar clusters, and trigger destructive tidal effects on planetary systems. The most massive confirmed wandering supermassive black hole weighs roughly 40 million solar masses and travels through intergalactic space between galaxy clusters. This cosmic leviathan could consume entire star systems if it encountered inhabited regions during its billion-year journey through empty space. Recoiling black holes strip material from their host galaxies during ejection events, creating trailing streams of stars and gas that extend for hundreds of thousands of light-years. These stellar wakes mark the paths of escaped monsters, like cosmic vapor trails visible long after the black holes themselves disappear into darkness. Some ejected supermassive black holes eventually return to galactic environments after billions of years wandering through intergalactic voids. However, these cosmic boomerangs often encounter different galaxies than their original hosts, potentially disrupting new stellar systems through gravitational interactions. The local group of galaxies containing the Milky Way and Andromeda likely harbors several wandering supermassive black holes ejected from smaller galaxies during past merger events. These invisible monsters drift through intergalactic space, completely undetectable until they encounter material to consume. Advanced alien civilizations would need galactic-scale monitoring systems to track wandering supermassive black holes and predict their approach to inhabited star systems. Early warning networks spanning millions of light-years might provide sufficient time for planetary evacuation or defensive measures. The upcoming collision between the Milky Way and Andromeda galaxies in roughly 4 billion years will create conditions for supermassive black hole ejection. Our galaxy's central black hole, Sagittarius A star, might receive a gravitational kick that launches it into intergalactic space, along with surrounding stellar populations. Future gravitational wave observatories will detect supermassive black hole mergers throughout the observable universe, providing advance warning of potential ejection events. However, the resulting wandering monsters might not reveal their presence until they begin consuming material billions of years later. However, these galactic-scale monsters seem almost gentle compared to the ancient relics from the universe's birth that may regularly punch through our solar system like cosmic bullets from the Big Bang itself. Ancient black holes created in the first moments after the Big Bang could be racing through our solar system right now at hundreds of miles per hour, invisible and undetectable, until their gravity reveals subtle effects on planetary orbits. You imagine black holes as products of stellar collapse that occurred billions of years after cosmic formation began. However, primordial black holes represent direct remnants from cosmic inflation itself, and some may weigh as little as asteroids while packing the gravitational punch of entire mountains. These cosmic fossils formed when extremely dense regions in the early universe collapsed under their own gravity before stars even existed. Unlike stellar mass black holes created from massive star explosions, primordial black holes can have any mass depending on the density fluctuations that created them. The smallest examples weigh less than Earth's moon, but compress that mass into regions smaller than atomic nuclei. Recent theoretical studies suggest that asteroid mass primordial black holes might transit our inner solar system roughly once per decade. These invisible visitors would follow hyperbolic trajectories at typical velocities of 240 miles per hour, crossing from Neptune's orbit to the Sun in just a few months. The gravitational effects of passing primordial black holes could create detectable perturbations in planetary orbits, particularly affecting Mars due to its lower mass and more eccentric trajectory. Computer models predict that asteroid mass black holes passing within Earth's orbital distance could cause meter-scale wobbles in Mars's position. Current spacecraft tracking networks achieve precision measurements of planetary positions accurate to within inches across interplanetary distances. This remarkable accuracy makes it possible to detect gravitational anomalies caused by invisible objects weighing as little as large asteroids passing through the inner solar system. The search for primordial black hole signatures requires analyzing decades of spacecraft navigation data for unexplained orbital perturbations that match theoretical predictions. Artificial intelligence algorithms can sift through millions of measurements looking for the subtle gravitational fingerprints of passing dark objects. If primordial black holes constitute significant fractions of dark matter, as some theories predict, they could be responsible for various unexplained astronomical phenomena throughout the galaxy. These invisible remnants might trigger stellar formation, influence galactic dynamics, and create gravitational microlensing events. The most dramatic primordial black hole encounters would involve objects weighing as much as Earth, but compressed to subatomic dimensions. Such monsters passing through the outer solar system could destabilize comet orbits, perturb asteroid trajectories, and potentially affect the giant planet's orbital mechanics. Laboratory experiments attempt to detect primordial black holes through their Hawking radiation emissions, but only the smallest objects produce detectable signals before evaporating completely. Larger primordial black holes emit negligible radiation and remain effectively invisible to electromagnetic observations. Future gravitational wave detectors might observe primordial black hole mergers that occurred when the universe was much younger and denser than today. These ancient collision signatures could provide direct evidence for primordial black hole populations and constrain their contribution to dark matter. The discovery of primordial black holes transiting our solar system would revolutionize understanding of cosmic inflation, dark matter composition, and early universe physics. These objects represent direct fossils from the first fraction of a second after the Big Bang, carrying information about conditions impossible to study through any other means. Advanced space-based gravitational wave observatories could potentially detect individual primordial black holes passing through the solar system by measuring space-time distortions they create. However, such observations would require technological capabilities far beyond current detector sensitivities. The abundance of primordial black holes remains one of the greatest mysteries in modern cosmology. While theoretical models allow wide ranges of possible masses and densities, observational evidence remains frustratingly elusive despite decades of searching. Some cosmological models predict that primordial black holes could cluster in dark matter halos around galaxies, creating concentrated populations near stellar systems. If true, our solar system might experience higher encounter rates than estimates based on uniform galactic distributions. The possibility that invisible primordial black holes regularly traverse our cosmic neighborhood adds another layer of hidden complexity to space environments that appear empty to conventional observations. Yet these ancient relics from cosmic inflation may already be revealing their presence through subtle effects that require only careful observation